In our last lecture, we introduced Newton's laws, and they basically were used to explain the orbits that Kepler found out. In this lecture, I'm going to delve a little deeper into those Newton laws, especially Newton's law of universal gravitation, but all of Newton's laws combined are gonna be used to explain several astrophysics observations, several astronomy and astrophysics observations. This is a picture of Earth with all of the satellites that are orbiting it, all of the human-made satellites that are orbiting it. Of course, the satellites themselves are greatly exaggerated in size. This is a picture from NASA from last year. So, of course, this is a computer-made picture. But think about it. Every single satellite that we launched into orbit, that's described here, is flying around Earth in orbits that resemble circles or ellipses that are kind of concentrated on Earth. So not only does Earth hold us on it using gravity, it also holds all of those satellites around it. Next few problems are related to that. What I'm trying to make you do with the next two questions is to actually solve an equation. Don't get scared, it's fairly easy. In the equation that you see in front of you, F is the force by Earth, gravitational force by Earth. G is the gravitational universal constant. M is the mass of Earth itself. Lowercase m is the mass of either satellite or itself. And R is the distance between the center of the Earth and that satellite or yourself. Now, think about all of those numbers on the right-hand side of the equation as being 1, and we'll just change one of them. So, if G is 1, M is 1, M is 1, and R is 1, the result of this is 1 times 1 times 1 over 1 squared, which is 1. Now let's see what that does once we change one of them. I'll give you about 20 seconds and try and figure it out. Then you can click to the next slide and you'll see the answer. Okay, hopefully the equation doesn't scare you as much anymore, because 1 times 2 times 1 over 1 is 2. Therefore, the force is twice the original force. That's all that was meant here. Let's try it again in the next slide. Okay, so look at the equation again. And this time around G is 1. The two M's are 1 each. And R starts as 1, but then goes to 1/2. So, instead of having F equals 1, what happens to the force now? 1 times 1 times 1 over half squared. Again, 20 seconds. You may have heard my cat meow in the background. That was not the answer. The answer is 4 times the original force, and that's because when you divide by a half squared, it's like dividing by a quarter. Dividing by a quarter is the same as taking something and multiplying it by 4. Okay? Basically, if you have a pizza and you divide it by quarters, how many quarters do you have? You have 4 quarters in a pizza, right? That's the general idea. That's about it. Give you a little bit of an idea of how universal gravitation works. Now look at this famous picture by Newton on how universal gravitation works. Basically, if You have a satellite or a cannonball flying from a tall mountain on Earth. If you have a force towards the center of the Earth that's a constant force, then all it does is it changes the direction of the satellite. Therefore, the satellite comes back and boom, hits you in the back of the head. Exactly 90 minutes later. What about if you shoot the bullet at a larger speed, or the cannonball at a larger speed? In that case, the motion becomes elliptical, and the reason for that is as you're moving further and further out, there is less and less of a force. Rather than having your little r being half, now little r is twice when we're talking about the ellipse at the very, very bottom. Now if you shoot the cannonball even faster, the ball may never come back at all, and the shape may be a parabola or a hyperbola. In the Tom Hanks movie Apollo 13, describing the mission of NASA to the moon, the astronaut in the film is saying, "Now Newton's at the helm." Indeed, flights from Earth, not just to the moon, but to some asteroids with the Dawn mission this year, and all the way out to Pluto with New Horizons, the one that we discussed in the forum, are using gravity assists. Not only are we launching from Earth, but we're using the moon and then some planets for gravity assists, which means due to the attraction to other planets, our probe would speed up, and of course those planets would slow down. They'll slow down so very little that it wouldn't affect them almost at all, but our wonderful spaceships would accelerate and reach places like Pluto in record time. In this particular picture, let's first of all concentrate on the moon and Earth and forget about the sun for a second. The part of the ocean that's closest to the moon, be it in quarter phase or in a full or new moon, the part that's closest to the moon is being pulled on by the moon the most. Earth itself is being pulled less, and the other side of the ocean is pulled less. Therefore, the side of the Earth closest to the moon has a bulge on it, then the Earth is pulled within the bulge, and the other side is has less of a tide. As a result, we have two tides in every direction. That's one way of describing this. Another is that you can look at the moon and the Earth as if they're kind of a heavy mass and a very low mass on a stick. The center of mass on which both of them would basically rest is slightly closer to the moon than the center of the Earth is. So from the center of the Earth, slightly towards the moon, that's where the center is. When the moon goes around the Earth, then the center of mass of those two is between the moon and the center of the Earth, and both of them are spinning around it. Therefore, it's kind of like holding a children's pool and holding it at one end and spinning it. And the children's pool kind of extends to make an oval shape. That side of the oval shape is closest to the moon is high tide near the moon. Then high tide on the opposite side of the moon also has high tide. If you have a person standing in there, think about, for example, the picture with the new or full moon. You have a person standing directly under the sun. That means it's noon there, as we had a few lectures ago. On the top, that's 6 p.m. On the other side, that's midnight. And on the bottom is 6 a.m. Therefore, if it's a new or full moon, you have high tide at noon or at midnight. Whereas if it's a quarter phase moon, you have a high tide at sunrise or sunset. Check it out, you're on your problem. Of course, the other thing that you may note is that when the sun and moon are working together, the tides are a tad higher. So when we have those very high tides at noon or at midnight, then that would be 4 feet above average, whereas high tides during quarter moon or third quarter moon will be only 2 feet above average. Now when you are in the Navy and you want to find out the time at which you would like to get into the harbor with the least chance of scraping the bottom, that would be during full moon or new moon. And preferably that would be at midnight or at noon. Check it out. That's the way the Navy learned about astronomy throughout its existence. We next discussed the effect called the precession of the equinoxes, which was the fact that the moon is trying to kind of straighten up the Earth. Earth's axis of rotation is tilted. The moon's orbit is tilted by a very little bit, less than 5 degrees, whereas the tilt of the Earth is 23.5 degrees. Therefore, the moon is trying to straighten the Earth up. That is, the bulge of the oceans is larger near the equator, at 23.5 degrees off from the ecliptic, the plane in which the sun is at. But the moon is trying to straighten it up. Now when you're trying to, for example, straighten up the wheel of bicycles that are turning around, it's very hard. Therefore, instead of straightening it up, it makes the whole bike lean. This is how you take a corner with a bike or with a motorcycle. This is exactly what happens with the moon and the Earth. The moon is trying to straighten Earth up, but instead of straightening it up, it actually causes it to precess, to move like a gyro. Here is a picture of how this happens. On the right hand side is a top trying to spin, but gravity trying to make it fall. As a result, it precesses. On the left hand side you see the Earth and the moon trying to straighten it up. Now in that picture we also have the inclusion of the sun. And the reason that this has been added is because just the moon would cause the precession. We don't need the sun for that. But the slight effect of the sun and the difference between neap tides and spring tides causes this effect to be ever so stronger when both the sun and the moon are doing their work together than during the rest of the month. Therefore, this would have a correction which creates some sort of a relationship with the months. See that in 2 slides. In this slide you can see the precession itself without the effect that's due to the sun. In this slide I remind you of where Polaris is. And in this slide you see the effect of the precession of Earth's axis of rotation. So right now Earth's axis of rotation is pointed towards Polaris, as it did for tens of years, as it will for the next tens of years. But over a course of hundreds and thousands of years, you can see that the axis is precessing. In 26,000 years it will be Polaris again, but in 13,000 years Vega will be the North Star. At the same time, vernal equinox is also precessing, and what happens is that the days and nights are equal, the vernal equinox, at this time when Earth kind of lines up with the constellation of Pisces. But it's gonna shift, it's gonna move towards Aries, etc. And it will move so that in 26,000 years it will again go in Pisces. Now think about it. That means that space has moved over the last 2,000 years. Therefore, a lot of those zodiac signs are not exactly where they're supposed to be. They're off by 2,000 years out of the 26,000, which is almost 1/12, which means almost a month off, which means that all of those horoscopes you were casting are different than they were 2,000 years ago. Uh-oh. Well, after all, astrology is a religion and not a science. Back to the effect of both the Sun and the Moon on Earth's precession. What happens is, because of the elliptic orbit of the Earth around the Sun and the Moon around the Earth, not only do we have a change that's due to the monthly effect, but also a change that's due to how close the Moon gets to the Earth, how close the Sun gets to the Earth, their closest. As a result, we're going to have this precession changing by a little bit. We will see that in the next slide. The following is a picture of the Earth's axis of rotation nutations. These are called general nutations. Those nutations are basically the wandering of the North Star, which is the North Star location, or the North Pole direction location as a function of time. This whole circle takes 26,000 years, but those little nutations, of course, take way less. On top of those, there is something called the Chandler wobble. An American astronomer in the 1890s figured out that the Earth's axis of rotation doesn't only follow those precessions and nutations, but also there is an extra wobble that we are not 100% sure we understand. The best model we have is that Earth itself does not have the axis go exactly through the center, but it's a little off-center, so Earth is not spinning exactly around its proper center. Think about a car wheel. You need to balance your wheels, and that is because they don't exactly spin around the very center due to the distribution of weight not being completely uniform. Same thing is true for Earth itself.